So the second problem for waves on a string, we shall consider this. This is x-axis, this is x equals 0. Here, two strings, but they have different mass densities, mass per unit length. This one has mu1, this has mu2, and I am sending a wave on this one to the right, and of course I am sending a harmonic wave. Those are the easiest. So last time we studied that it is traveling. The question is, it comes to here. There is a discontinuity here. And then another string continues from here. So something happens here. So what can happen? Part of the wave that comes will be reflected. Part of it will be transmitted. So the thing to compute is what fraction of energy is reflected back and what fraction of energy is transmitted forth. So this is what we shall do. Let me remind you of the wave equation. So we have two regions now, 1 and 2. In both regions, and we have y1 and y2. Both of them solve this equation. But the crucial thing is that they oscillate with the same omega. So what is invariant in this problem is omega. The oscillation frequency is the same. Second, tension is the same, because if tension was different here than here, it would move. So tension is the same. What is different is the velocity of the u01 and u02. These things are different. So omega is u01 k1, that's equal to u02 k2, and this is root t over mu1 k1 t over mu2 k2. So therefore k1 over k2 is root mu1 over mu2. Since k1 is 2 pi over lambda 1, it's inversely proportional to the, so wavelengths are different. So depending on the relative magnitudes of mu1 and mu2, the wavelength of the wave changes. Part of the wave is reflected back, and part of it is moving with a new wavelength. Reflected wave will have the same wavelength because it's on the same medium. So this is the problem we shall solve. Let us say that why? Because this is tension. Because omega is the same, we can take in both cases y of xt is equal to psi times e to the minus I omega t, and del square y equals 0 means this gives me an omega square. That means psi plus k square psi is equal to 0. Well, I did it too quickly. This is only a function of x. This is a function of time. So del square, let me do it, delta x square times e to the minus I omega t minus 1 over u0 square psi of x times minus omega square times e to the minus I omega t is equal to 0. Therefore, omega square over u0 square is k square, minus minus is plus. So we have e to the minus I omega t times psi. This is now a total d psi dx because psi depends only on x. So we shall solve really for these psi's. So with that preparation, we now try to solve this problem. Namely, we shall, the solution is here, we guess. The solution here we guess. And then we have a matching condition at x equals 0. So one condition is obvious. Namely, if it is oscillating like this, for example, both of them have the same displacement. So transverse displacement. So the displacements at the point of discontinuity must be the same. I'm erasing and then we shall start solution. Solving the problem. All right. In the region 1, y1 is e to the I kx plus r e to the minus I kx. Let me call it psi 1. Of course, y1 is psi 1 times e to the minus I omega t. All right. So when you multiply by e to the minus I omega t, this is a wave that is going to the right. This is a wave that is going to the left. I could have used multiplied here by a, but this is only a scale because I am really interested in the fraction of energy that is reflected back and transmitted forth. So this arbitrary strength is not important. So we just replace it by 1. So this is psi 1. And psi 2 is, this is K1. I am in the region 1. K1 and K2 are different. So this is T e to the I K2x. That is, this is x smaller than equals 0. This is x less than 0. So the first condition, we have to, there are two unknowns in this problem. K1 and K2 are known. And the unknown things are R and T. The amplitude of reflection and the amplitude of transmission. One equation is obvious at x equals 0. Psi 1, 0 is equal to psi 2, 0. That means 1 plus R is equal to T. But there are two unknowns, and this is only one equation. We need another equation. And one wonders, what about the derivatives? So remember the wave equation. Let me just write it like this. Del square y delta x square, that's equal to mu del square y delta t square. Let me multiply, let me integrate this equation x0 from x0 minus epsilon to x0 plus epsilon, where x0 is arbitrary. I have an infinite string. X0 is an arbitrary point on this string. So I multiply by dx, integrate from x0 minus epsilon to x0 plus epsilon t. I can take it out. It's constant. So it is, this is ky. This is d by dx of delta y delta x. And this integrate because integrates. So this is simply t times delta y delta x at x0 plus epsilon, since t is constant, minus delta y delta x at x0 minus epsilon. The difference in the derivatives. This will be equal to, I multiply this thing, mu dx, integral from x0 minus epsilon to x0 plus epsilon, del square y delta t square. And if I take epsilon to be very small, that means I take the acceleration at x0. So I have mu times 2 epsilon times del square y x0 t delta t square. So this term equals that. However, if I let epsilon go to 0, this part, this is delta m, delta m goes to 0 with epsilon going to 0. So if this difference is finite, the only way to make the right-hand side finite, as this thing goes to 0, is to make this infinite. But no system can go through an infinite acceleration. So this really goes to 0. That means at any point, in particular, x0 could be the point of discontinuity here. X0 could be 0. So that means the derivative will be continuous. dy dx is continuous. So this says that the displacements are the same. This says that the derivatives are the same. This will give us the second condition. Second equation from which now we can use this one and the next one to find R and T. So I'm erasing this part. I hope you are convinced the derivatives, space derivatives must be equal. Now it's gone. So we have 1 plus r equals t, because then we have psi 1 prime at 0 is equal to psi 2 prime at 0. So this, take the x derivative, I k1 1 minus r. Namely, I take the derivative, then put x equal to 0. So these things disappear. That's equal to the derivative of the outgoing wave, transmitted wave. That's ik2t. So i's cancel. So let me write here. We have two equations. 1 plus r equals t, and k1 minus k1r is equal to k2t. So it's an easy equation to solve. Multiply the first one by k2. k2 plus k2r is equal to k2t. k1 minus k1r is equal to k2t. Subtract. This is 0. This is k2 minus k1 plus k2 plus k1 r equals 0. Therefore, r is equal to, this goes to the right hand side with a minus, k1 minus k2 over k1 plus k2. So we found the reflection amplitude, the coefficient in front of e to the minus ik1x, coefficient in front of the wave of unit strength that is moving to the left. So t is equal to 1 plus r, k1 plus k2. So it is 2 k1 over k1 plus k2. So we found these coefficients. Let me just erase this. Now we know the displacement must be equal at this point, and x derivative, space derivatives must be equal. So we found R, let me just write it here, K1 minus K2 over K1 plus K2, and T is 2K1 over K1 plus K2. All right, I am erasing it. But we have not answered the question yet. If I am sending energy per unit time along this to the right in the first string, how much of energy is reflected back and how much of energy is, what percentage of the energy is going ahead to the right. And for that I have to look at the time averaged energies. So I have an, for example, we discussed I, E average was rho E U 0, and we said this is A square, the amplitude square, times 1/2 omega T, this is the tension, times K. Okay? So we shall make use of it. So we have three energy currents. One is the incident, one is the reflected, one is the transmitted. So IE incident is equal to A is 1. Here we put 1. So I have 1/2 omega T times K1. Remember, omega and tension are invariants in this problem. They are not changing. So only K is changing. IE reflected is, well, now we have R. So absolute square of that times 1/2 omega T, and again K1. So IE reflected divided by IE incident, how much of the energy is reflected back is divide this by that, but they have the same K1, same omega 2 over T, so it is simply R square. So let me call it R. This is the fraction of energy that is reflected back, reflection coefficient, and that's equal to K1 minus K2 over K1 plus K2, K1 plus K2 square. Let's look at the IE. These are all time averages. Let me just, to shorten notation, put a bar. I is equal to I bar. This is shorter to write than. So I bar E transmitted is equal to the coefficient square, absolute square, that's T absolute square, times 1/2 omega tension times K2. Therefore, how much? What's the percentage that is moving forth? How much of the incident energy is moving forth? So it is simply IE transmitted divided by IE incident. So this thing cancels. I have T square, but K2 over K1. So if I put T absolute square, so let me write like this, K2 over K1 for K1 square over K1 plus K2 square equals, this knocks it off, 4 K1 K2 over K1 plus K2 square. So to that we shall call T, transmission. We have too many T's. One we use for period, one we use for tension. Now it's for the transmission coefficient, but I think this is the transmission coefficient, T. Transmission coefficient. An interesting thing to observe is this relation. I can erase these, at least this part I can erase. Notice that R plus T is equal to, when you square it, this gives me minus 2k1, k2. This is plus 4k1, k2. So when you add them, it is k1 plus k2 square. So it is k1 plus k2 square over k1 plus k2 square is equal to 1. Well, of course, what do you expect? We define them as IE reflected over IE incoming plus IE transmitted over IE incoming. That's equal to 1. Namely, we accounted for all the currents in this problem. That's unitarity. Namely, we followed the energy in all its paths. We can make a simple graphical representation of the energy flow. This is the point at x equals 0. Current IE incident comes in. Current IE transmitted goes out. And of course, these are in the same direction, same line. But let me draw it like this. IE reflected. No energy accumulates at x equals 0. Energy is not sucked in at x equals 0. So what comes in goes out. The incoming energy current, just like the electric current. For example, you have an electric current that divides I1. I divides between I1 and I2. There are resistors, etc. So, looked at this way, the picture is simple. The incoming energy is... So, you can multiply. Remember, we wrote psi1 as e to the I kx plus r e to the minus I kx. We could multiply it by a, some strength. It doesn't matter. When we take the ratios, those strengths go away. So the question is, how much, what percentage of the energy, incoming energy, is going into is transmitted or reflected. So R and T are the percentage of energy, the fraction of energy that is reflected or transmitted. If it were a quantum mechanical problem, and there's a very quantum close analog to it, for example, a wave coming to a potential step, it has the same mathematics, except there you will say the probability. Here we will say the fraction of energy. Before we pass to the next problem, let me just point something here. If K1 is equal to K2, which means mu1 equals mu2, then reflection coefficient is 0. And this is 4k squared over 4k squared, t equals 1. So if mu1 equals mu2, then r equals 0, t equals 1. Another thing is that if K1 is very much larger than K2, meaning that mu1 is very much larger than mu2. So if mu1 is very much larger than mu2, then r is 1, t equals 0. But same is true for the other limit. If if mu2 is very much larger than mu1. Also, if mu2 is very much larger than mu1, then again r equals 1, t equals 0. R goes to 1, let's say. This goes to 0. All right, so these are the two limiting cases. Thank you.